Next image enhancement task we want to look at is deep blurring. We have an original image that has sharp contrast, and the image has been blurred somehow with some point spreading function, and we cannot actually see the sharp contrast anymore. For example, the image on the left has sharp contrast and very strong boundaries. On the right-hand side, the image has been blurred somehow, and we see that actually the contrast differences is lowered. So we want to go from this blurred image back to the sharp one. We will see two approaches. One of them is unsharp masking, and the other one is inverse filtering. Unsharp masking is a simple but effective method. It's image independent, and effectively, it's a linear method. Even today, this simple method is used in photocopiers and scanners around the world. The idea in a sketch looks something like this. Assume that we observe the red curve right here. We can see that this is not a very sharp profile. It has been blurred somehow. It's a smooth transition now. What we want to do is we want to smooth the curve first to obtain the black one, and then look at the difference between the red and the black. If we add this difference to the original curve again, we see that actually we can increase the gradient between the two parts and really sharpen the profile. And the idea is really this simple. The principle is a bit different. We want to interpret the image as actually a snapshot of a diffusion process. And we've seen the diffusion process when we studied anisotropic diffusion filtering. We remember that it led to Gaussian filtering. We will now look at a diffusion process with constant diffusion coefficient. We will make a first-order approximation to this partial differential equation and say that, you know what, the image at a certain time t, as it has diffused according to this partial differential equation, can be given with the original image that was sharp and not blurred, plus some differences that's actually multiplied and the difference increases by time. Now, if we put the definition of the time derivative here, we see that actually the original image can be retrieved back as the smoothened image at time t minus the second derivative of the smoothened image times a constant with ct. So the unsharp masking produces the output O from I simply by taking the second order derivative, the Laplacian operator of I, and multiplying by a well-chosen constant k. How do we estimate the second order derivative of I? Now that's actually a tricky problem because if we naively estimate the derivative of I, we will actually be prone to error. Instead, we will look at differences of Gaussian approximation. Essentially, we will first smooth the image and then take the derivative. Or, since both of them are linear operators, we can combine them and we can simply convolve with a mask in 2D, the Mexican hat mask that's shown here. This actually approximates first Gaussian smoothing and then taking the second order derivative. And in our 1D example, this is exactly what we've done. We've basically smoothed and then took the difference between the images. So the unsharp masking idea really takes the input image, subtract from the second order derivative the Laplacian, and gets the sharp one. We see that the edge profile becomes steeper, giving a sharper impression. And notice that this is not a perfect method. We have some under and overshoot flanking at the edge, and further increases the impression of the image sharpness, but this is a perception issue. So let's see some results. We have here an image that we want to see the plate number, for instance. It's blurred. If we apply unsharp masking, we can see that actually we can increase the contrast in the image and the plate number becomes more visible. I think the difference especially becomes visible if you look at the derivatives or if you look at the sharp edges in the image. And notice that the method also increases the amount of noise. And that's normal because it doesn't really understand the difference between a real edge and noise. So if you can actually detect it with a Laplacian filter, if its noise is big enough, then it will get unsharpened with the operation. The second operation is called inverse filtering, and it relies on the system view of image processing. It is a frequency domain technique, and it's defined through the modulation transfer function. And it really will create the links to more theoretically optimal approaches like the Wiener filtering we will see next. The idea is quite simple. As I said, it's a frequency domain technique, and assume that you know the modulation transfer function of the blurring operator B. I will call it the BU of V of the blurring filter. Now, the input image I has been blurred by B, so it's been convolved in image space, and we got the image that we observed. In the frequency domain, that basically means the frequency of Fourier transform of the image times the Fourier transform of the blurring kernel will give me the Fourier transform of the observed image. So to undo the effect of the filter B, what we can do is we can use a new filter with the modulation transfer function B prime, such that if I multiply B prime with B, I get the identity. So multiplying F with B prime, I should get the input image, the sharp image that I was looking for. A very simple idea would be to use B prime equals to 1 over B. Now, for additive noise after filtering, this might actually cause some problems, because if I now divide F with B, and I will always have noise, for example, we had noise in the car image as well. If I multiply F with B, see that I basically get the I here, that's the Fourier transform of the image, but I also get the Fourier transform of noise divided by the Fourier transform of the blurring kernel. Now that's a bit problematic, because assume that the blurring kernel for some frequency pairs is very low, and that will be the case for any low-pass filter. For example, in the higher frequencies, they will have a lower value. Well, noise, as we know, has equally strong values in all frequencies. So in high frequencies, actually, this division will become very large, and that will actually give us the main problem with the inverse. That will actually bring us to the main issue with the inverse filtering. Sorry, I wrote problem, but it should be filtering. So the frequencies with BU of V close to 0 or 0, they will actually lead to information loss. So they cannot be brought back after filtering. So essentially, the inverse filter is an ill-defined problem. So when I do this, effectively, I basically take this noise and amplify it whenever BU of V is very small. So that's actually a problem, because you see that I don't get the image back at the edge locations on the high frequencies. Instead, I will get the noise response amplified. Let's see a 1D example. We have this very strong profile that has been convolved with a very small box filter, and the output is given by this. Now, if I do deblurring, the noisy version using inverse filtering, I get some very abrupt responses. Here I have the image added by noise. After inverse filtering, I amplify the noise quite a bit. If the initial noise level is larger, I can see the profile here, but I actually see the noise as well. If when I deblur it, I don't get the original sharp image back. Instead, I get complete noise, because actually the noise amplification dominates the response. What does it look like in the image? I took the image that we've seen before, and I applied Gaussian smoothing, for example, with a standard deviation of 16 pixels, so quite a large blurring to the image, and we see that the image has been blurred. Now, let's assume I apply inverse filtering to this, and this is the response I get. You see, actually, I get a very large number of spurious high frequencies that were not there before. Let's see that again. I have the blurred image, and these image pixelation artifacts become huge after inverse filtering. And it is true that in certain areas, for example, the eyebrows, the nose, and the boundaries with the hair in the background, I see some sharpness after the inverse filtering. But the noise amplification is so much, the resulting image is actually not pleasing at all. Now, the optimal way of doing this is actually not inverse filtering, but using Wiener filtering. The idea is we consider the amount of noise amplification in areas where the filter response is low. So it's actually a much better version of the inverse filtering. And you can derive the entire thing through an optimization formulation, and we will not go into that now. And nice thing is filter is given analytically in the Fourier domain, just like the inverse filtering itself. Now, the Wiener filter takes this form here. So the H prime, which corresponds to the B prime of the inverse filter, is actually given by this form, where H is divided by the H conjugate times H plus 1 over SNR, the confidence term. Remember, SNR was the power spectrum of the image over divided by the power spectrum of noise. So what does that form do actually? Let's assume that we are not looking at the case that was problematic before. So really H is becoming 0. So whenever for example, if we talk about the blurring filter, the high frequency components will be killed. So H is 0. And in the inverse filtering, I will be multiplying the image with 1 over H and do noise amplification these locations. However, the Wiener filter, when H is 0, actually takes the value of 0. So it will not do noise amplification at all. It will still do blurring. It will still kill those frequency components. When SNR is infinite, meaning that I am sure that actually there is no noise and the image signal dominates the entire Fourier spectrum, then 1 over SNR is going to 0. So I'm very confident. In that case, the Wiener filter actually converges to the inverse filtering in the no-noise case. So it's actually converges to the ideal thing. But when SNR is 0, meaning that I'm really sure that there is no real signal in that part of the spectrum, but rather only noise, then SNR goes to 0 and 1 over SNR goes to infinity, leading again Wiener filter to go to 0. So it's actually quite a nice behaving filter. Let's see how it does. I again look at the same structures. I had the original sharp image here. I blurred it with a small box filter to get this. Now, I want to retrieve the image after adding some noise using the Wiener filtering. And obviously, in the Wiener filtering, I can choose the SNR level. So let's assume that I have medium confidence, meaning that I have medium SNR assumption across the entire spectrum. You see that if I actually now do apply the inverse filtering, I get the image or sharp image back a little bit. Now, of course, there is the effects of noise. That's really difficult to get rid of. But if you compare it with what we got in the inverse filtering, this is quite a good result. Now, assume that I have no noise. I have very high confidence. And the SNR assumption means that I have SNR going to infinity. Then in that case, if there's no noise, I can actually almost get the actual actual profile back. So that's actually quite pleasing. Now, if we look at the noisy results with different SNRs or different confidence levels, now given the noise image here, if I have very low confidence, assuming that, you know what, I'm not really sure if there is any signal, it's mostly noise, the Wiener filter doesn't really change much the profile. It tries to sharpen it a little bit, but not that much. If I assume medium confidence, so almost the correct SNR, I see that there is some noise amplification, but the profile is sharper as well. So it's doing a decent job. If I assume high confidence, like the case in the inverse filtering, then I get the same result as the inverse filtering. Noise amplification dominates the result. Now, let's look at this image again, and we want to basically, starting from the same image with the same Gaussian smoothing, we apply Wiener filtering and get the sharp image back. So let's look at this result again. We see that the Wiener filtering does a very good job actually removing the blurring here and sharpening the image. Of course, this is not the original image back, but still, it does a quite a good job. Now, problems in applying Wiener filtering exist as well. We know that the output is actually the Wiener filter times the actual blurring filter times I. So effectively, the filter that we apply to the actual image is the Wiener filter times H. In the ideal case, this effective filter should be 1 so that the output is the same as the original sharp image. Now, if we talk about conservative, meaning that if SNR is low, this actually tends to become a low-pass filter. So the Wiener filter with low SNR assumption will actually blur the image instead of sharpening it. Now, SNR, it's really something difficult to know because it actually depends on the power spectrum of the image and the power spectrum of the noise. So actually it depends on the power spectrum of the original sharp image, which we do not know in the first place. Moreover, so we cannot know the SNR, we have to make some assumptions. Moreover, we don't actually know the filter as well. We can only make certain assumptions. And if we don't know the filter perfectly, the result of the Wiener filtering will be quite bad. So the actual original blurring filter should be somehow estimated pretty accurately for Wiener filter to work well. The last topic we want to cover in image enhancement is the contrast enhancement. We observed an image with bad contrast, either under or overexposure, and we want to get the actual image back. Now, there are really two use cases. One of them is compensating under or overexposure, and the second one is if an image actually uses only a small portion of the available intensity ranges. That's not really interesting. We want the image, most of the image, to cover an intensity range or the very large scale of the intensity range. So we want the interesting part of the image to be quite visible with very high contrast. There are several methods to deal with this, but we will work with the most obvious one or the most well-used one, which is the histogram equalization. First, we want to define what a histogram and a cumulative histogram is. Let's assume that we start from this case where we have an image, and that's the very sharp image that we've seen before with very well contrast. Now, if I look at the intensity values that ranges from 0 to 256 and count the number of pixels at each intensity, I get back the histogram of the image. Now, this is an approximation of the probability density distribution of the image, of the intensities, if I assume the image to be formed of independent pixels. Just like a histogram and a PDF, I can also actually create a cumulative distribution or a cumulative histogram. That basically means that I start from 0 and integrate until 255. And this will give me the cumulative distribution going from 0 to 1. Now, if I look at an image with very bad contrast, the histogram and the cumulative histogram of this image will be very different. Specifically in this case, I have the background pixels, so I have lots of zeros here in the orange histogram. But I see that most of the intensity values tend to be very high. So they will actually be concentrated in the larger intensity areas here. So I see that there are no not a lot of pixels with intermediate intensity values and a lot of pixels with very high intensity values. Just like the histogram, I can see the same effect in the cumulative histogram as well. Now I have the background, so I shoot up as I take the integral of the histogram. Then there is some stable region for a while, and very high intensity values have very high number of pixels, so the cumulative histogram increases quite rapidly. How do we correct it? We use intensity mappings. Effectively, we basically try to create monotonic mappings between old intensity and the new intensity. And we can use generic transformation functions like the one that's given here, or we can use power law transformations. Using such input to output mappings, we will try to correct the histogram. And the method, the histogram equalization, has a very simple principle. Given an image, we want to convert the image intensity such that in the end, we obtain a flat histogram. The cumulative distribution function or cumulative histogram or flat histogram will basically look like a simple line without any changes, just a ramp. How do we do it? We find an appropriate intensity map depending on the image content. And the method that we create, although it looks like it will depend on the image content, will actually be quite generally applicable. So let's first see what it can do. Given an image like this, if I apply histogram equalization out of the box, I can actually convert this image into this. Now you see that actually I increase the contrast of different areas quite a bit. So that's actually quite nice. The license plate here is now much more visible with the numbers really darker and the background on the plate is much brighter. If I look at the brain image, if I apply histogram equalization, I can really get back the contrast between the different tissues. So that's quite nice. How does it work? The idea is to redistribute intensities one to several or one to one in the continuous case, keeping their relative order. So use a monotone mapping. So I want the old intensities here. I want to create a map to new intensities. The mapping actually is trivial to find. It's quite easy. It actually corresponds to the cumulative intensity probability or cumulative histogram. So the mapping is just this guy. And this is, as you can see, it's a monotone map. And I basically go from the old intensities to the new intensities. Now, obviously, there is some difference here because the old intensities are going from 0 to 55, and the output of the cumulative distribution function goes from 0 to 1. So I will have to correct for the global scale. But let's first the idea here. So let's assume that on the right-hand side, I have the old cumulative distribution function of an image. So the intensities are going from 0 to I max, and I have the distribution. And the cumulative distribution function is going from 0 to 1. What do I want to do? I want to use this cumulative distribution function as the mapping. So on the right-hand side, on the left-hand side, I basically draw just an identity map. So you can imagine that using cumulative distribution function, meaning that I simply map the intensity values here to the intensity values right here. So for any intensity, I compute the cumulative distribution function of it, or cumulative histogram of it, and simply multiply it with the I max to keep the range from the minimum to maximum in the new image as well, and use that value as the new intensity. The mapping itself looks something like this. I prime, the new intensity values, is T of I, which is actually I max, the maximum intensity value of the old image, times the cumulative distribution function of that intensity value. This cumulative distribution function in the continuous case can be computed simply by taking the integral of the probability distribution function from 0 to I, 0 being the minimum intensity value in the old image. That's actually this simple. There's nothing really more. So I have the actual cumulative probability distribution function and the target probability distribution function. And notice that this left-hand side is the cumulative distribution function of the new image. And you see, it's a ramp. So its histogram will be simply flat. Let's see mathematically how this actually works. Suppose we're actually in the continuous domain, so we have the probability distribution function of the original intensities. Our mapping was this guy here. So to be able to compute the histogram of this, or the probability distribution function of this, we can simply use the change of transformation forms in the probability distributions. So P of I prime is actually equal to P of I times the Jacobian of the transformation between I and I prime. In this case, since everything is one-dimensional, it will be di over di prime. Now, using basic integration formulas and the derivatives, we know that this actually is 1 over P of I times 1 over I max. As P of i's cancel, the probability distribution of Pi prime is 1 over I max. It's a constant, so it's indeed a flat distribution. That will be all for this week. I hope to talk to you more next week. Have a good evening.